I wanted to start by going over the formulas for some of the measures of dispersion we talked about in the last video. I wanted to go over the formulas for population and sample variance and for population and sample standard deviation. These formulas use the symbols that we went over in the last video. So I'll remind you what the symbols stand for. This is the formula for a population variance. It's x minus mu, this Greek symbol that looks sort of like a U. It's actually the sum of that squared over capital N. Now what is this formula saying? The x minus mu means a data value minus the population mean. Remember that this mu symbol right here stands for the mean of a population. So what this formula is saying is to subtract each data value, each x, by the population mean, and then square the answer. So that's the step that we did when we subtracted each value by the mean and we squared all the answers. This right here is a summation symbol. What it's saying is for us to add all of the squared answers. And when we calculated the population variance in the last video, one of the steps that we did was adding all of the squared answers. What this n on the bottom is saying is to divide the total of the squared deviations by the population size, by the number of people in the population. The capital N stands for the number of people in the population. So when we divide the total of the squared deviations, which we have on top, by the population size on the bottom, we get the average or the mean of the squared deviations, which is the population variance. Let's now talk about the formula for the sample variance. It's a similar formula, but some of the symbols are a little bit different. X still means an individual data value. It's x minus x bar squared over lowercase n. So notice how this symbol has changed to an x bar, and this symbol right here, this uppercase n, has changed to a lowercase n. Now why has it changed? Well, x bar is a symbol for a sample mean. When you calculate a sample variance, you're subtracting each data value by the sample mean, by the mean of the sample. So the mean is an x bar instead of a mu. And when you calculate a sample variance, you're dividing the total of the squared deviations, which is up here, by the number of people in the sample. Actually, I'm sorry, you don't divide it by the number of people in the sample. You divide it by the number of people in the sample minus 1, because the sample variance has an adjusted formula in which you don't divide by the number of people in the sample, you divide by 1 less than the number of people in the sample. So this formula is telling us to subtract each data value by the sample mean and square the answer, square each of the answers, and then add all of the squared answers, and then divide the total that you get on top by 1 less than the number of people in the sample. Remember, the lowercase n is the number of people in the sample, and 1 less than that number is n minus 1. Now what about the formula for population standard deviation? I'm sorry, I should have said population variance and actually I did write it out correctly. Sorry, I thought I made a mistake, but I didn't. Remember that the population standard deviation is just the square root of the population variance. If you take the variance and go one step further and get the square root, you get the standard deviation. So to get the formula for the population standard deviation, we just take the variance formula, we take the population variance formula, and put it under square root sign, like this. So if we take the population variance formula and put it under the square root sign, we get the formula for population standard deviation. What about the formula for sample standard deviation? Well, the sample standard deviation is the square root of the sample variance. So we just take the sample variance formula and put it under the square root sign. And there's our formula. What this formula is saying is that if you want the sample standard deviation, just take the sample variance and find the square root of the sample variance, and that equals the sample standard deviation. What you have to do to get the sample standard deviation is use this formula to calculate the sample variance, and then go one step further and get the square root of the sample variance. And these are the four formulas that I wanted to cover. Next, I wanted to show you how to calculate some of these values in Excel. What I did was I took the spreadsheet we had on the board last time, and I put it into Excel. First, let's get the mean of each of these columns. These three columns are quantitative, and these two columns are qualitative, so we can actually only find the mean of the three quantitative columns. So how can we do that? Excel calls the mean an average, which is fine because mean and average mean the same thing. So what Excel wants us to do is to type in an equal sign, and then type in the name of the value that we want to calculate. The value that we want to calculate is an average, so we type in average. Then we put a parentheses right there, a left parentheses, and we highlight the column that we want to calculate the average of, and then we put a closing parentheses right there, and then press enter, and it gives us the mean, meaning the average of this column of data. And if we want to get the mean of these other two columns, we can put the mouse right there at the bottom right corner and drag it across, and it actually automatically calculates the mean of this column and the mean of this column. Just to see what happens, we can try to drag it across and see if it can calculate the mean of these two columns. It's probably going to give us an NA. Right, it can't calculate the mean of a list of words. So you can't get the mean of a column of qualitative data. What about the median? We can get the median of these columns. Well, we can have a median of these first four columns. Remember, you can have a median for quantitative data or for ordinal data, but not for nominal data, which we have over here. So to get the median, we can type in equals, and then the word median. Put our left parentheses right there. Highlight the first column on the left. And then we put our closing parentheses and then press enter. And if we drag it across, it'll give us the medians of these two columns. Let's see if it can calculate the median of a column of ordinal data. First, let's just take a look at it to see what the median would be. If we put these in order, it would be freshman, freshman, sophomore, junior, senior. So the middle value would be sophomore, so the median should be sophomore. Oh, okay, so Excel can't calculate the median of a column of ordinal data, so we can just type in the word sophomore, since that is the median. Now what about the mode? To get the mode of these columns of data, we can type in equals mode, and it has two choices. It says mode multiple or mode single, or just mode. I think we should probably just click mode right there and put our parentheses, highlight the column, and then press enter. I think I made a mistake. I typed in the wrong parentheses. We can drag it across to get the mode, to get the modes of these columns. I'm not sure if it can calculate the mode of a column of ordinal or nominal data. We'll drag it across and see what it does. No, it can't do it. What about the range? Well, I don't think Excel has a function that can get the range, so we might have to do it on our own. The highest value here is 40, and the lowest value is 18. So 40 minus 18 is 22. That's the range. Over here, the highest is 15 and the lowest is 12, so the range is 3. And over here, the highest is 2, the lowest is 0, so 2 minus 0 is 2. What about mean absolute deviation? Excel calls the mean absolute deviation the average deviation. So it's AVE-DEV. Type in the left parentheses. Drag it across, and the H column has more spread or more dispersion compared to these two columns. Notice how in this column the numbers are spread out all the way between 18 and 40, and over here in the number of units column the numbers are pretty similar. They all fall between 12 and 15, and over here the numbers are all pretty similar, meaning close together. They're all between 0 and 2. So the mean absolute deviation should be the highest right here, and it should be lower here and here, because it comes out to a higher number when the column has more spread. So yes, it did come out much smaller over here compared to when we calculated it with the H column. The same thing will happen with the variance and standard deviation, because they also measure the spread of the data. For variance, we have to type in equals VAR. See how it says VAR.P and VAR.S? One of these is the population formula, which doesn't have the n minus 1, and then the sample formula, which does have the n minus 1. Let's say that this data is from a sample, because it's a pretty small set of data, and most data sets that people collect are from samples. So we'll say that it's a sample and choose VAR.S. Let's highlight this column. Let's drag it across. So the variance did come out higher here and lower over here and here, because it comes out to the highest number when the data has the most spread. For standard deviation, we would type in equals STDEV.S. This is for sample. So it'll come out to the highest number here, and it'll come out to lower numbers over here because these columns are less spread out. Right, so that is what happened. And over here we could enter in the median and mode, and over here we could enter in just the mode, because a set of nominal data has a mode only. So sophomore is the median. What's the mode down here? The mode is the value that shows up the most number of times. So Freshman shows up twice, the other values only show up once, so the mode is freshman. And what's the mode over here? It looks like each value only shows up once. Psychology, sociology, engineering, business, engineering. No, engineering shows up twice, and every other value shows up once, so the mode is engineering.
This is the same spreadsheet that we had in Excel. I showed you how to summarize a set of data with descriptive statistics. Now I want to show you how to summarize a set of data by creating tables and graphs. And the tables and graphs that I'm going to show you how to create in this video are meant to display something called frequencies. Now before we get into creating the tables and graphs, let's talk about what the word frequency means. The frequency of a value is the number of times the value appears in the data set. So let's look at the number of times 30 appears in the age column. 30 appears once in the age column, so the frequency of 30 is 1, because the age of 30 only appears once in the data set. Let's look at the number of units column and look at this value of 13 units. The value of 13 units actually shows up twice in the data set because we have 2 people who are taking 13 units. So we would say that this value has a frequency of 2, and it looks like 2 people are taking 12 units, so this value of 12 units would have a frequency of 2 because it shows up 2 times. So the frequency of a value is the number of times it appears inside its column of data. Now let's talk about how to display frequencies in a table or in a graph. And the way that we present the frequencies actually depends on what type of data we have. It depends on if it's quantitative or qualitative. If we have a column of qualitative data, we would present the frequencies in something called a bar graph. And let's create a bar graph for the grade level column. We need a line for the x-axis. So the values that appear in the grade level column are freshman, sophomore, junior, and senior. So we'll put those values down here. We'll put those words down here. I'll have to make the font smaller so it can fit. This is freshman. This is sophomore. Junior and senior. We need to have a y-axis that'll show the frequencies. We'll just put some tick marks on the y-axis. Now what's the frequency of freshman? Well, freshman appears twice. So what we would do is we would make a bar going up to 2 right here. And how many times does sophomore appear? Sophomore only appears once in this column of data, so since sophomore has a frequency of 1, it goes up to the first tick mark. This just shows that it appears 1 time. What about junior? We have one junior in the data set, so it has a frequency of 1. And senior also appears once, so it also goes up to the first tick mark. So we just created a bar graph of this column of data for grade level. What about for this other column right here, for college major? We could also create a bar graph for college majors. Whenever you have a column of qualitative or categorical data, you can create a bar graph. We'll talk about what to do when you have a column of qualitative. We'll talk about what you do when you have a column of quantitative data after we finish with these two columns of qualitative data. So let's put the values down here. And since it's a column of nominal data, the values don't have a clear order to them like they did over here. Since this was a column of ordinal data, it was clear what order we should put these values in.
What we'll have to do is just choose an order to put these values in. We can just follow the order from top to bottom. So we'll put psychology first, and then sociology, and then engineering, and then business. So let's find out what the frequency of psychology is. Psychology appears one time in this column, so its frequency is 1. So go up to the first tick mark. What about sociology? It also appears once. And engineering appears twice. So this will go up to the second tick mark. And then business appears once, so it goes up to the first tick mark. And we've created a bar graph for the grade level column and a bar graph for the college major column. And I said that you create a bar graph when you have a column of qualitative or categorical data. There's a different type of graph that you would make for a column of quantitative data. And the graph that you would make for a column of quantitative data looks like a bar graph, but it is actually a little bit different. And I'll show you why. The graph that we would make for a column of quantitative data is called a histogram instead of a bar graph. When you make a histogram, you start with a number line, like this, and then we would start with the lowest value right here, which is 0. We would mark off all of the different values that appear. The only values that appear are 0, 1, and 2. So we don't even need this extra part of the number line out here. We can just stop once we pass the highest value. And then we'll create a y-axis for the frequency. I should probably move 0 over a little bit just so it's not so close over here. So 0 has a frequency of 2 because 0 appears twice in this column. So this bar will go up to 2. And what about 1? Well, 1 appears once in this column, so it has a frequency of 1. So it goes up, this little bar will go up to the first tick mark. One difference between a histogram and a bar graph is that in a histogram, the bars touch each other. So this bar would actually be touching right here. And the frequency of 2 is 2 because 2 people have 2 children. This value appears twice in this column. So this bar will go up to 2. So one difference between a histogram and a bar graph is that in a histogram, the bars touch each other, and in a bar graph, they're separated from each other. And also in a histogram, you have numbers on the x-axis down here. And in a bar graph, you typically have words down here, or categories. So these two graphs would be called bar graphs. This one would be called a histogram. So this is a histogram for number of children. We can also make a histogram for number of units. I'll move this down a little bit so we can see that it's separated from this graph over here. We'll make a number line for number of units. The lowest number is 12 and the highest number is 15, so our tick marks will go from 12 to 15. What's the frequency of 12? 12 appears twice, so it has a frequency of 2. We'll go up to 2 right there. 13 shows up twice, so it has a frequency of 2. What about 14? 14 doesn't appear at all, so it has a frequency of 0, so we'll just leave this blank. What about 15? 15 appears once, so this will go up to the first tick mark. Whenever you have a value like this that has a frequency of 0, you just leave it blank. And we don't include any values that are below the lowest value or above the highest value. That's why we didn't include 11 and we didn't include 16. But when you have a value in between the highest and lowest values that has a frequency of 0, you just leave a gap in the histogram like we did here. So this is for number of units. I'll move these over so I have more room. Now let's make a histogram for age. Here we have a column of numbers where it's not very easy to make a histogram like we did here, where we just mark off all of the different whole numbers between the lowest and highest values. The reason why is because the values go all the way from 18 to 40. So it would be a very long graph if we marked off every number between 18 and 40. So what we can do instead is we can create groups of numbers. I'll show you what I mean. 18 is between 15 and 20. So maybe instead of just marking off 18, we could mark off 15 to 19. And then next we could mark off 20 to 24. So we're doing intervals of 5 numbers at a time. I'll move this over so we have a little bit more space. Next we would have 25 to 29. And then after that we would have 30 to 34. And then after that we would have 35 to 39. We'll keep going until we pass the highest value. Looks like the highest value is 40, so we need one more interval. Each of these groups is called an interval. The technical word is actually a class interval. We'll talk about that word more later. So we need one more class interval, which will be 40 to 44. And we don't have any values that are above that interval, so we can stop there. We don't have any numbers between 45 and 49. And we also don't have to go any lower than this because we don't have any numbers between 10 and 14 because 15 is the lowest number, so we can stop here. We don't have to go any lower than this interval. So now we have to count how many numbers appear between 15 and 19. In this column of data, in the age column, how many numbers are there that are between 15 and 19? Well, looks like only one number because 18 is the only number that's between 15 and 19 in this column. So this interval down here has a frequency of 1. It contains one number. So we'll go up to the first tick mark. Next we have to find out how many numbers are there in the age column between 20 and 24. Well, 21. Looks like 21 is the only number that's between 20 and 24. So there's two numbers that are between 20 and 24. So this goes up to the second tick mark. What about 25 to 29? We don't have any numbers between 25 and 29, so it has a frequency of 0. It'll just be a gap. And we have one number between 30 and 34, which is just 30. So this has a frequency of 1. We don't have any numbers between 35 and 39, but we do have one number between 40 and 44, which is just 40. So this will go up to the first tick mark, because if we have one number, then we go up to tick mark number 1. And people often talk about the shape of the histogram, or the shape of the bars in the histogram. I'll show you what I mean by the shape. If we outline the bars in each of these histograms with a curve, we'll see that each of these histograms has a certain shape. Let's do it with this first histogram right here. We'll outline the bars with this green curve. We can see that this one has kind of a wavy shape that has a curve that goes up and then goes down and then goes back up again, kind of like a camel. And this one has a shape where it goes up and it peaks at the left end and it goes down and then it goes up again and then down again. This one would have this type of shape where it has a long flat area, then it goes up, it has another peak, and then it goes down and it's flat again, and then it has one more peak over here. And they've actually given names to the different types of shapes that can appear when you make a histogram. And next I'll go over what the different types of shapes are and what their names are. First I wanted to remind you that these two graphs were called bar graphs because they were created with columns of qualitative data, and these three graphs were called histograms because they were created with columns of quantitative data. And each of these 5 columns of data has its own frequency graph. So age had its own graph, number of units had its own graph, and each of the other 3 columns had its own graph. So if you have 5 columns, you'll have 5 of these graphs. If we had 7 columns, we would have 7 graphs, and so on. One type of shape that you can have in a histogram is called a normal distribution. And normal distribution is usually called a bell-shaped curve. A normal distribution and a bell-shaped curve have the same meaning, and in daily life you probably hear the word bell-shaped curve more often. I'll show you what that type of shape looks like. It just follows a bell like this. This is a normal distribution, meaning a bell-shaped curve. This is when the bars start off short at the left end, and then they gradually become taller, like this. Then they peak in the middle. And then they start to gradually trail off toward the right end. You can see that this normal distribution curve is just outlining the shape of the bars. So whenever you see a normal distribution curve or a bell-shaped curve, just realize that it's just outlining the shape of the bars in a histogram. Okay. In a normal distribution, the values that are near the center, meaning the more medium values, have the largest frequencies, and the values that are at the low end down here have lower frequencies, meaning they don't appear as often, and the values that are higher up here also have lower frequencies and they don't appear as often. One type of variable that often follows a normal distribution is IQ. With IQ scores, most people fall into the middle range of IQ scores in here, and then fewer people are at the low end of IQ down here, and then fewer people are at the higher end of IQ up here. Height also tends to follow this type of a curve, where most people have medium heights in here. So heights between, let's say, 5 feet and 7 feet might have the tallest bars in here, and then there would be fewer people who were shorter than 5 feet tall, and fewer people who were taller than 7 feet tall, at least if you're talking about adults. So we know what a normal distribution is. Now what about a shape that doesn't follow a normal distribution? Next we'll talk about the different types of non-normal shapes, meaning the shapes that don't follow a normal distribution. One possibility is to have a histogram that peaks further to the left than a normal distribution does. So you might have a shape like this that peaks near the left end, where the lower values appear more often and the higher values appear less and less often in the data set. So we can see that it peaks too far to the left to be a normal distribution. And this type of a shape would be called skewed to the right. And I'll tell you why it gets that name. It's actually either called skewed to the right or positively skewed. It involves the direction that the graph is trailing off toward. So we can see that the bars are trailing off toward the right end down here, meaning it peaks at the left end and then it gradually trails off and gets shorter when you go toward the right end. So just imagine this arrow going down to the right, and that's why it's called skewed to the right. And you can also think of it as it's trailing off toward the positive end of the number line, so it's positively skewed. Now what about the opposite type of graph? What if it peaks at the right end and then trails off to the left? The reason I'm putting a normal curve here is just to show you how it doesn't follow a normal curve. So when I draw this normal curve right here, this normal distribution, you can see how the shape of the bars doesn't follow this type of shape. So we'll make one that peaks at the right end like this. And then trails off toward the left end. If we make an arrow, we can see that it's trailing off toward the left end. So it's called skewed to the left, or negatively skewed, because you can imagine how it's trailing off toward the negative end of the number line. So it's negatively skewed. And you might be thinking that it should be the opposite, where it should be that if it peaks at the left end, it should be skewed to the left, and if it peaks at the right end, it should be skewed to the right. But it's actually not named that way. It's actually the opposite of what you would think it would be. The word skewed to the right actually refers to the direction it's trailing off toward. It doesn't refer to the side of the graph that it peaks at. So if it peaks at the left end and trails off to the right, it's skewed to the right. If it peaks at the right end and trails off to the left, it's skewed to the left. You might imagine if this was a mountain and you were stuck up here at the peak of the mountain up here, if you would rather walk down to the right down the right side of the mountain, meaning if it would be easier to walk down this side of the mountain at the right end, then it's skewed to the right. And if you were stuck up here and this was a mountain, and if it was easier to walk down to the left end, then it's skewed to the left. There's two other types of non-normal shapes I wanted to talk about, meaning when I say non-normal, I just mean shapes that don't follow a normal distribution. You can also have a graph that peaks lower than the normal distribution and a graph that peaks higher than the normal distribution. And we'll talk about those next. I'll copy and paste the normal distribution down here. just so we can have it to compare to these other graphs. Let's imagine a type of graph that's flattened out, kind of like a pancake, or more like a pancake, where maybe it's not perfectly flat, but it's more flattened out than a normal distribution is. Something like this. Maybe not like a pancake, but more like a butt cake. So we have a graph that's flattened out like this, and it peaks lower than the normal distribution. This more flattened type of shape would be called a negative kurtosis. It's kind of a strange word, but it's called a negative kurtosis. You can think of it as the word negative as meaning it peaks too low. So it might help you remember the name if you think negative means peaking lower than a normal distribution. If it peaks higher than a normal distribution, it's a positive kurtosis. What a positive kurtosis actually is when you have longer tails. I mean, the curve stays flatter longer, like this, and then it suddenly, or it more suddenly, becomes taller, like this. So instead of going up gradually, it stays flat longer, and then once you get closer to the center, it goes up more suddenly. And then it goes up higher than the normal distribution, so it might even go up this high. And then it goes down suddenly again, goes down pretty quickly, and then it becomes this flat tail down here. So we have these flat tails, and then we have this sort of sudden peak in the middle, this sudden tall peak in the middle. It's kind of like you're taking a normal distribution and squeezing it inward like this, where if this was a ball of dough, or like Play-Doh, I guess, if you pushed inward from the two sides, the peak would move in like this, and it would move up higher, and that would give you a positive kurtosis. A negative kurtosis would be like if you had a normal curve made out of Play-Doh and you pushed down on it to smash it down, and it became a flattened shape like this. It's just one way to think about it. So if it peaks lower than the normal curve, it's a negative kurtosis. If it peaks higher than the normal curve, it's a positive kurtosis. And negative kurtosis is more flattened out like this. And in a negative kurtosis, the heights of the bars are more similar. We don't really have a peak that really stands out very much. But in a positive kurtosis, we have a peak that stands out a lot. The peak is more distinct than in a normal distribution because you actually have this tall and narrow peak that appears in the middle of right here in the graph. So actually in a negative kurtosis, the peak of the graph is flatter and wider than the normal distribution. And in a positive kurtosis, the peak is narrower and taller than in the normal distribution.